All right, in this video, we're going to talk about 9.1. We're going to use the same problem from section 2.6 that we talked about last time. I'll leave this work for that problem up on the screen. This is number 4 from section 2.6. This problem has been worked out as an example in section 9.1 is why I'm using it. So you don't have this work there. That's why I'm providing this work for you. But what I'm going to do in Excel, they provide the table for you there as well. I encourage you to try to do some of these calculations by hand, since you probably won't have Excel at your disposal if you have to do this on a test. But I assume that your teacher is probably going to minimize the number of steps for you to need to take, and keep the function relatively simple for you in order for you to do this on a test. If it is a in-class portion of the test, more than likely this would be some kind of project or take-home assignment or something like that, though, that you would work on this with lots of time so that you can show all of your calculations. Again, I think that it would be okay to ask your teacher if you could do this in Excel so that you have all that type of automation. But again, our f of xy here is going to be our differential equation that was given to us of 2xy. We were given the initial conditions that when x is 1, y is 1, and we're trying to approximate the value of y of 1.5 using linearization here, using tangent lines. So we came up with the equation y equals e to the x squared minus 1 as our exact solution to this initial value problem. And we know that we can use Excel here to find exactly what y of 1.5 is, but we're going to use an approximation technique that improves on the approximation technique that we used last time from section 2.6. And the key difference is that we're going to say that we know that the tangent lines that were the slopes that we're using are off, and we eliminate a lot of that error by averaging slope values together to get a better approximation. So let's go ahead and open this up. I've made an exact copy of what we did before. And the only thing in our table that we need to change, all the formulas are copied as well over here so that it's looking at the same reference values. The only thing that I need to change is this formula right here. And it's a little messy, but bear with me. So I'm going to leave the reference value here of this one, and then plus 0.1 here is good, but we're going to multiply times the average of this value that we've already calculated, and then we're going to calculate a new one, which is 2 for our problem, because it's 2xy for our f of xy, 2 times, and we're going to use this x value here, and we're going to use a y value of our old y value, so in parentheses, old y value plus 0.1 times our 2 times old x value times old y value. And this is on the first step what we would have gotten here, but we're multiplying, we're putting that into our equation here and finding the average, and you'll see we get 1.232 which is great. Let's go ahead and drag that down now, and you'll see that all of our y values are going to update to those that are in the table here. So we have 1.5479, 1.9832, 2.5908, and 3.4509 as our new approximations for y. That new approximation for y at when x is 1.5 of 3.4509 is much closer to the actual value of 3.4904. It's only off by 1.13% now as compared to our first technique that we used from 2.6 was off by 16.12%. So let's go ahead and let's see if we can get that even better by using more steps like we did before and letting our h, our delta x, be 0.05 instead of 0.1. So let's copy and paste here. And again, I'm going to change this formula here to be times the average of, and this one is going to be same function 2 times, but I'm going to take this x value times, and then in parentheses, we're going to have old y value hang on a second, I'm in the wrong place. Let me go ahead and do this up here times the average of 2 times, there we go, new x value times, and then we have old y value plus h times previous x value times previous y value. Close that up for that new approximation for y, close that up for the average, and we should have $1.1077 is pretty good. Okay, let's run this down. 3.4795 is our new estimate here, and compare that to 3.490 3 for our actual value. We get a absolute error of 0.0108, a percent error of 0.31%. Now that is really good. So this improved technique where we find a better approximation of y by using the average of a couple of slopes where the formula looks like this. Let me come back and show you the formula for this. So in 2.6, our formula looked like the regular linearization formula that you have had since calculus, that y sub n was equal to sorry, y sub n plus 1 was equal to y sub n plus hf of x, y, and these were sub n's. So you used the previous values here to calculate the next one. So this was our easy method from 2.6, but it had a lot of error. 9.1 tells us that we should use y of n plus 1 is equal to y of n plus h times the average of f of xn, yn, and f of xn plus 1, yn plus 1 star, where y of n plus 1 star is equal to yn plus h f of xn, yn. It's that same formula as before, but we're continuing to use these new, better calculated values as we go through. So you're not using all of the old y values. That's not what it is. You're using what your projected value would be here and averaging it with your old value to get a better approximate value. So you know your projection is off, you have your old value, and you say the better estimate is somewhere halfway in between that projection and that old value. And you do that and then multiply that times your delta x and add it to your old y value to get a better estimate. So come back to the Excel sheet again, and we'll see how we did way better both times with only 5 steps. We're even better off than we did with 10 steps in our old method. See, we were at over 9% error with our old method, even with 10 steps last time. With only 5 steps here, we're just slightly above 1% error, which is really good. But when we went to 10 steps here, we were below 1/3%. So 0.031%, really, really good. So why do we need to know this? Because we can't always get exact solutions with all of these methods that we've done. Sometimes so far, we've done nice problems that we know methods to be able to get our answers. Sometimes we just can't get an answer. We know that an answer exists. We can't get a closed form for exactly what that answer would be. And sometimes this type of approximation technique is good enough. And we say we can tell you that an answer exists, but we can't put our finger on it, but it's really close to this value, and hopefully that value is good enough. So depending on what your application is for needing this value, maybe a 9% error isn't that bad for you. I'm not saying that it's going to be 9% all the time, but maybe this is good enough of an approximation. But if you're trying to do something with a lot of precision and accuracy, then maybe you need to use this improved form. And when there's automation, like that's what I was showing you with Excel, is if you were doing all this by hand, you would want to reduce the number of calculations you needed to make and the number of steps and so on and so forth. But there's really no reason to not use technology like this when you're using this technique, to not take 100 steps and make your answer very, very precise. So you could even go as far as to write a little bit of code and to automate this process even more than what I did with the spreadsheet. But I don't think at this point, in where we are with technology, that you should be trying to do all this on the back of an envelope, with a bunch of rounding, um, because you're going to get rounding error on top of rounding error on top of rounding error. If you do that, you should go ahead and you should use a graphing calculator, or even better, use an Excel spreadsheet like I was using, that can keep track of all the exact values and can give you the most precise answer possible, because that is kind of our goal in this. We're getting an estimation, but we want as good of an estimate as we can get. Okay, so that wraps up all of the core content for this class. This was the last main objective, and I do plan to come back and do some bonus content for this class after I finish up some linear algebra videos for you. Since it requires a little bit of linear algebra, I'll go back to the linear algebra videos, then come back to this class later. But if you were to take the 400 level version of this class at a university, the main differentiation between that 400 level class and what you did in this 200 level class is the content from chapter 8 that we didn't cover, that requires some linear algebra. I'll come back and I'll do that separately, so that it's not included and will not look like part of the core content of this. But watch out for those videos if you're interested in them. They're not going to be something that your teacher is going to probably cover or put on your exam or anything like that, but it will help you see how we can do things, solving systems of differential equations using matrices. And it's quite analogous to things that we did in our homogeneous differential equations, and finding answers for non-homogeneous differential equations, and all those types of things that we did. What happened with our three cases when we had distinct solutions, and we had repeated solutions, and we had complex solutions, but you need to know some stuff about eigenvalues and eigenvectors and things like that from linear algebra before you can understand those concepts. So bonus content coming, if you want to look for that in the future. But hopefully you enjoyed this content, and look forward to, maybe if you have other classes that you're going to take, to have those videos up for you as well. But we're going to stick mostly to videos for developmental 100 and 200 level classes. So more than likely, this is one of your last math classes that you would be taking at the 200 level. So good luck with whatever you're doing, and good luck on your exam at this point, because that should be forthcoming after you would be done watching this video.